Welcome to the Late Lab. It's a pleasure to have you here. Before anything else, there's always a quiet curiosity about where these videos find people. Maybe this is playing in a dark room at the end of a long day. Maybe it's keeping company on a late journey home. Maybe it's just you, a blanket, and a few peaceful minutes stolen from the noise. Wherever this reaches you tonight, hopefully you're warm, settled, and ready to let the mind wander a little. If these slow explorations are the sort of thing you enjoy, giving the video a like and subscribing does help this little channel keep glowing softly in the background. And if you're already subscribed, thank you. Genuinely, it helps more than can easily be said. Now there is a small risk with tonight's subject. It may sound like exactly the kind of thing designed to lull the mind into a peaceful daze, right up until physics quietly reveals that even empty space is not truly empty, and that what seems like nothing may be one of the busiest parts of reality. Not ideal for sleep, perhaps, but undeniably interesting. So with that pleasantly unsettling thought in place, let's ease into it. Why is empty space not really empty? And what does that strange fact reveal about the hidden structure of the universe? Most people have a very simple idea of nothing. Nothing is the empty room after everyone has gone. Nothing is the silence before a sound begins. Nothing is the gap between objects, the dark stretch between stars, the blank place where no thing appears to be. It feels straightforward. A cup can be full or empty. A shelf can hold books or hold nothing. A pocket can contain coins, lint, or, on unlucky days, absolutely nothing useful at all. In ordinary life, emptiness usually means absence. Something has been removed, and what remains is simply not much. That instinct is practical, and for daily life it works perfectly well. A person does not need quantum theory to know when the biscuit tin is empty. The tragedy announces itself clearly enough. But physics has a habit of taking these comfortable everyday words and quietly revealing that they are less stable than they seem. Empty turns out to be one of those words. It behaves nicely in conversation, then becomes much more troublesome the moment science starts asking what, exactly, has been removed, what remains behind, and whether a place can ever be truly free of physical content. This is where the trouble begins. In daily language, empty often means empty enough for present purposes. An empty room still contains air, dust, light, heat, drifting molecules, and perhaps a sock that vanished 3 months ago and has only now reappeared beneath the bed. But no one objects to the phrase. The room is empty because no people are in it, or because the important things are gone. The word is flexible. It is shaped by convenience. Physics is not always so forgiving. Once a scientific question is asked, the meaning has to tighten. Empty space can no longer simply mean a place that looks blank to human eyes. It has to mean something more precise. Does it contain matter? Does it contain air? Does it contain radiation? Does it contain forces? Does it possess structure? Can anything happen there? These are not poetic questions. They are technical ones, and each answer changes what emptiness really means. For a very long time, people argued over whether a true void could exist at all. The ancient Greek philosopher Aristotle rejected the possibility of a vacuum in the strict sense. In his view, nature did not permit a true emptiness. The phrase often associated with this tradition is that nature abhors a vacuum. Whether nature feels emotional revulsion is, of course, another matter, but the idea carried weight for centuries. Aristotle believed that a completely empty space was not a stable or even meaningful feature of the world. Motion, place, and matter were all bound up together in ways that left little room for a literal void. Later thinkers treated the matter differently. As natural philosophy slowly became modern science, the question of emptiness stopped being only a matter for abstract argument and became something that could, in principle, be tested. That change was profound. A void was no longer just an idea to be debated in a courtyard. It became something people might try to produce, measure, and understand. By the time Isaac Newton entered the story, the picture had shifted again. Newton imagined space in a far more definite way. In classical mechanics, space could act like a vast stage on which matter moved and forces operated. Even when no objects were present in a given region, space itself still existed as a kind of framework. It did not need to be filled with visible substance in order to be real. That was already a major change from older ways of thinking. Empty space, in this view, could be meaningful and physically relevant even when it contained no obvious matter. That may sound ordinary now, but it was a quiet revolution. It meant that emptiness was no longer just the absence of things. It could be a location with geometry, distance, direction, and measurable consequences. A cannonball crossing a field, a planet circling the sun, a pendulum swinging in a hall. All of these depended on space being treated as something real enough for laws of motion to operate within it. The stage might be bare, but it was still a stage. Even so, classical emptiness remained fairly calm. If a region contained no matter, no smoke, no dust, no moving objects, and no light passing through, it was tempting to imagine that region as deeply quiet. Not mysterious, not active, just empty. A clean container with the contents removed. That classical image is important because it shaped intuition for generations, and in many ways it still shapes intuition now. When most people hear the phrase empty space, that is what comes to mind. A clean, still background. A gap, a blank. The difficulty is that nature does not always respect the neat categories that language prefers. As physics developed, each new layer of understanding made empty space slightly less empty. First, scientists learned that removing visible matter was not the same as removing air. Then they learned that removing air was not the same as removing radiation or fields. Then came deeper questions still. Questions about whether space itself might have properties even in its quietest possible state. That is why the idea of nothing has to be handled carefully. Nothing in ordinary speech is often just a useful shortcut. Nothing in science has to survive closer inspection. The moment the inspection begins, what looked like a blank may turn out to contain structure, laws, and hidden activity. The ordinary meaning does not disappear, but it stops being enough, and that may be the strangest part of all. Human intuition tends to imagine reality becoming simpler as things are taken away. Remove the furniture, remove the air, remove the dust, remove the light, and surely what remains must approach pure absence. Yet physics keeps finding that the deeper the search goes, the less simple emptiness becomes. Silence is not always silence. Blankness is not always blankness. And nothing, examined closely enough, begins to look less like a void and more like a question waiting patiently in the dark. Once the idea of nothing began to move out of philosophy and into science, the question changed in a very important way. It was no longer only whether empty space could exist in principle. It became whether emptiness could be made, observed, and measured. That may sound like a small shift, but it changed everything. A philosophical void could be argued about forever. A laboratory vacuum, on the other hand, had to do something. It had to leave evidence. It had to affect an instrument. It had to behave in a way that made the invisible visible. This is where the old, comfortable meaning of empty began to narrow into something more precise. In ordinary speech, empty often means that nothing important remains. In physics, that is nowhere near strict enough. A glass that looks empty is still full of air. A room that feels empty still contains gas molecules rushing about at hundreds of meters per second, colliding endlessly with one another, and with every wall, chair, and sleepy person inside it. Even a clear patch of sky is not remotely empty in the scientific sense. It contains particles, radiation, and the physical effects of gravity and electromagnetism. So the first serious scientific step was not to discover a perfect void, but to distinguish apparent emptiness from a state in which matter had been removed as far as experiment allowed. That is how the idea of vacuum became so important. A vacuum is not merely a poetic nothingness. It is a region where the amount of matter, especially gas, has been greatly reduced. That sounds simple enough, but achieving even that required a major change in understanding. For many centuries, air itself was not fully recognized as a material substance with weight, pressure, and measurable effects. It was just there, quiet and taken for granted like wallpaper for existence. Once scientists began to understand air as a real physical thing, the possibility of partially removing it became meaningful. Pressure was the key. Gas pressure comes from countless molecules moving and colliding with surfaces. In air at sea level, Every square centimetre of surface is under a steady push from the atmosphere above. It does not feel crushing because the body is adapted to it and because pressure acts in all directions at once. But it is enormous all the same. At sea level, atmospheric pressure is about 101,000 pascals, which means each square metre experiences a force of roughly 100,000 newtons. That is comparable to the weight of several family cars pressing down over the area of a small table. The atmosphere is polite enough not to announce itself dramatically most of the time, but it is always there. Evangelista Torricelli helped reveal this in the 17th century with one of the most elegant experiments in early physics. Torricelli filled a glass tube with mercury, sealed one end, inverted it into a dish of mercury, and observed that the mercury in the tube fell only part way. A column remained suspended. Above it sat a space with no ordinary air in it. This was one of the earliest laboratory demonstrations of what came to be called a vacuum, though not a perfect one in the modern sense. The crucial point was that the mercury was not being held up because nature disliked emptiness, but because the atmosphere pressing on the dish supported the column. The height of the mercury column, about 760 millimeters at standard atmospheric pressure, provided a way to measure that pressure. It was a remarkable achievement. A region that looked empty had become part of an instrument. The vacuum above the mercury was not just an absence. It played a role in an experiment with a definite, repeatable result. That was a profound change in the history of emptiness. The blank space had become operational. Blaise Pascal pushed this understanding further. He recognized that if the atmosphere was supporting the mercury column, then the height of that column should change with altitude, because there would be less air above at higher elevations. That prediction was tested by carrying a barometer up a mountain, notably the Puy de Dôme in France. The mercury column fell with increasing height, just as Pascal expected. The air itself had weight. Atmospheric pressure was real. The vacuum in the tube was not a philosophical curiosity. It was part of a measurable system governed by physical law. There is something quietly delightful about this stage of science. A question that had once invited grand declarations about the nature of existence was being settled, at least in part, by glass tubes, liquid metal, and people trudging uphill with equipment. Reality often behaves like that. The deepest questions do not always announce themselves with thunder. Sometimes they arrive inside a barometer. This was the beginning of a more disciplined idea of emptiness. A vacuum was no longer defined by vague absence. It was defined by what had been reduced, how much had been reduced, and what measurable consequences followed. That distinction matters enormously. Removing matter from a region is not the same as removing all physical structure from it. A vessel pumped free of most of its air may contain very few atoms compared with ordinary conditions, yet it still has volume, boundaries, temperature, electromagnetic influences, and later in the story, much more besides. Even a very good vacuum is not automatically a featureless void. Modern vacuum chambers make this clear. In laboratories today, engineers and physicists can create ultra-high vacuum systems with astonishingly low particle densities. In some cases, the pressure can be reduced by more than 10 orders of magnitude below atmospheric pressure. That means the number of gas molecules left inside is tiny compared with everyday air. Yet the chamber is not nothing. It still has walls. It still exchanges radiation. It still sits in spacetime. It still obeys physical laws. A near vacuum is not the erasure of reality. It is a controlled environment in which certain kinds of matter have been drastically reduced. That distinction prepared physics for deeper questions. Once a vacuum became an environment with measurable properties, scientists could stop asking only whether emptiness existed and begin asking what emptiness was like. Could it transmit light? Could it host fields? Could it affect motion? Could it be altered by geometry or energy? Those questions would become increasingly important during the 19th century and beyond, especially as the study of electromagnetism, relativity, and quantum theory made the background of the universe seem less like a passive blank and more like something with structure of its own. So the journey from void to vacuum was not merely a change in vocabulary, it was a change in method. The old idea of nothing had been broad, intuitive, and slippery. The newer idea of vacuum was narrower, testable, and tied to instruments, gases, and pressure. It taught physics an enduring lesson. Empty does not mean what it seems to mean at first glance, and once the search begins in earnest, the space left behind after matter is removed does not become less interesting. It becomes more so. By the time physics began to mature into a precise mathematical science, space had settled into a remarkably calm role. It was often treated as the great background of everything else. Matter moved through it. Forces acted across it. Events unfolded within it. But space itself in the classical picture did not seem especially busy. It was there, certainly. It had distance, direction, and extension. It allowed one object to be here and another to be over there. Yet it was usually imagined as passive, almost silent, like a stage after the actors have taken their places and the scenery has been fixed. That image proved enormously useful. A stage does not need to explain the play. It simply provides the setting in which the play can happen. In much the same way, classical physics often treated space as the framework within which motion could be described cleanly. A planet orbited the sun through space. A cannonball arced through space. A pendulum swung through space. The interesting part seemed to lie in the bodies themselves, in their masses, positions, speeds, and the forces acting between them. Empty space, by contrast, appeared to be what remained when nothing occupied a region. Useful, yes. Real, certainly. But not especially active. Isaac Newton gave this picture its most influential form. In Newtonian mechanics, space and time provided the stable arena for motion. Newton spoke of absolute space, meaning a real, unchanging framework that existed independently of the objects within it. Even if every planet, stone and speck of dust vanished, space itself would still remain. It would not collapse for lack of furniture. It would continue as the great container of all possible positions and motions. This was a powerful idea because it made physics beautifully clear. Motion could be described relative to a stable background. Rest and movement were no longer just matters of local appearance. A body could accelerate, and that acceleration could be treated as objectively meaningful, not merely relative to nearby objects. Newton's laws worked extraordinarily well under this view. They described falling apples, rolling carts, ocean tides, and planetary orbits with astonishing success. Classical space, calm and indifferent, seemed to do exactly what a good background should do. It stayed out of the way. There is something deeply attractive about that simplicity. Human intuition likes a world in which the backdrop behaves itself. It is reassuring to imagine that the universe contains objects and events, while the empty parts between them remain blank and obedient. That picture feels clean. It feels economical. It feels almost polite. Space in this view does not intrude. It simply hosts. Yet even within classical physics there were hints that the background might not be as empty as it seemed. Newton himself described gravity as acting across space, but he was cautious about claiming to know the deeper mechanism behind that action. How could the sun influence Earth across roughly 150 million kilometers of apparent emptiness? How could one body affect another without direct contact? The laws predicted the effects superbly, but the idea still carried a slightly haunting quality. Something was happening across space, even if the nature of that happening remained obscure. Later thinkers questioned whether space should be treated as absolute in quite the way Newton imagined. Gottfried Wilhelm Leibniz argued for a more relational picture, where space was not a thing in itself so much as the network of relations among objects. In that view, empty space separated from all matter was a less meaningful concept. The debate between absolute space and relational space did not end quickly, and in truth, it never disappeared entirely. But for practical physics, Newton's version dominated because it worked so well. For a long while then, empty space retained its classical calm. If a region contained no visible matter, it was tempting to think of it as physically uneventful. A vacuum might be difficult to produce, but once produced, it could still be imagined as a bare section of the stage. Remove the actors, remove the props, and all that remains is the quiet floorboards beneath them. That expectation is important because it shaped what scientists thought emptiness ought to be, and the shock of later physics depends very much on how ordinary and still that older emptiness once appeared. The situation began to change more dramatically in the 19th century with the rise of field theory. James Clerk Maxwell played a central role in this transformation. Maxwell unified electricity and magnetism into a single framework, showing that changing electric fields and changing magnetic fields could sustain one another and travel through space as electromagnetic waves. Light itself turned out to be one of these waves. This was not a small adjustment to the classical worldview. It meant that what crossed empty space was not merely the motion of solid particles, but structured, measurable disturbances in something more continuous. At first, many physicists imagined that waves required a medium. Water waves move through water. Sound waves move through air. So if light was a wave, what exactly was waving? This led to the idea of the luminiferous ether, a hypothetical medium thought to fill all space and carry electromagnetic vibrations. The ether was meant to preserve an older kind of comfort. Empty space would not be truly empty after all. It would be filled with an invisible substance whose sole apparent purpose was to let light behave sensibly. That idea eventually ran into serious trouble. But even before its downfall, something important had already happened. Physics had begun to treat extended entities in space as real. A field was not just a bookkeeping device. It was a physical quantity with values at every point in a region. An electric field could exist in what looked like empty space. A magnetic field could stretch across a vacuum chamber. Light could travel through regions containing no ordinary matter. The blank stage was no longer entirely blank. It had become capable of supporting patterns, influences, and propagation. That shift matters enormously. Once a field is accepted as physically meaningful, the line between empty space and physical content begins to blur. A region without atoms might still contain an electromagnetic field. A vacuum might still permit waves to pass, forces to act, and energy to be distributed across space. The old image of emptiness as complete stillness becomes harder to defend. Space starts to look less like a passive container and more like a domain in which physical quantities can exist, evolve, and interact. Even so, the classical field picture still preserved a certain orderliness. Fields could be smooth and continuous, space remained intelligible, and causes produced effects in ways that, while sometimes subtle, still felt broadly stable. The world had not yet tipped into quantum strangeness. Nothing was yet flickering in and out of existence. The vacuum had not yet become restless. But the ground beneath the older idea of emptiness was already shifting, and that is the crucial point. Before empty space could become strange in the modern sense, it first had to stop being a mere absence. Classical mechanics treated space as a calm arena. Classical field theory began to populate that arena with real extended structure. Once that happened, the vacuum could no longer be understood as simply nothing at all. It had become a place where measurable things could exist without ordinary matter being present. The stage was starting to acquire a life of its own, and physics was only just beginning to notice. For a while, classical physics managed to keep space in a fairly modest role. It was the backdrop, the arena, the quietly reliable setting in which matter moved and forces did their work. But in the early 20th century, Albert Einstein began to dismantle that comfortable picture. Space was not going to remain a silent stagehand. Time, too, would lose its separate status. In their place came something stranger and more unified. Spacetime. The name matters because the concept matters. In Einstein's physics, space and time are not independent containers. They are woven together into a four-dimensional structure in which events occur. A location is no longer fully described by where something is. It must also include when it is. That may sound almost obvious now, but it represented a fundamental shift. The universe was no longer a collection of objects moving through a rigid grid. while a universal clock ticked evenly in the background. The grid and the clock had become part of the same physical fabric. Einstein first developed special relativity in 1905. That theory applied to motion at constant speed and showed that measurements of time and distance depend on the observer's motion. Two people moving differently can disagree about how long an interval lasts or how far apart two events are, and yet both can be correct within the structure of the theory. The speed of light in vacuum remains the same for all inertial observers, and the laws of physics take the same form in all inertial frames. Those two principles force space and time into a more flexible relationship than Newtonian intuition ever allowed. Already this was enough to make the background less rigid. Time could stretch, length could contract. Simultaneity, which sounds so absolute in everyday life, turned out to be partly dependent on perspective. Events that appear simultaneous to one observer may not be simultaneous to another moving differently. The universe was beginning to look less like a theatre with fixed seating and more like a structure whose measurements depended on how one moved through it. But special relativity still left gravity outside the picture. Einstein's deeper leap came with general relativity, completed in 1915. This theory replaced the old Newtonian idea of gravity as a force acting across space with a geometric description. Matter and energy tell spacetime how to curve, and curved spacetime tells matter how to move. That sentence has become famous because it captures something truly radical. Gravity is not simply an invisible pull passing through emptiness. It is the shape of spacetime itself. That change is difficult to overstate. In Newton's universe, space was the fixed arena, and gravity acted within it. In Einstein's universe, the arena itself can bend, stretch, and evolve. The background is no longer separate from the drama. It joins the cast. A useful image is to think less of space as an empty hall and more as the geometry that defines possible paths. Near a massive body, such as the Sun, spacetime is curved. Planets do not orbit because they are being tugged by a mysterious invisible rope. They follow the straightest available path through curved spacetime. Those paths are called geodesics. In ordinary flat geometry, the straightest path is what people usually picture as a straight line. In curved geometry, that idea becomes more subtle. The path can be natural and unforced while still appearing bent from a wider point of view. This means that even a region with very little matter in it may still possess structure. A stretch of deep interstellar space can have geometry. A region far from stars can still lie within a curved space-time shaped by distant mass and energy. Empty, in the older everyday sense, is no longer enough. The absence of nearby objects does not imply the absence of physical properties. A calm-looking region may still carry the imprint of gravity through its geometry. General relativity also allows space-time to behave dynamically. It is not merely curved in a static, frozen way. It can change, it can expand, it can ripple. Entire cosmological models arise from this fact. The universe itself is not sitting inside a larger empty box while matter drifts around within it. In the standard cosmological picture, space is expanding. Galaxies are not mostly flying through pre-existing emptiness like sparks through the air. Rather, the distances between large-scale structures grow because the geometry of space-time evolves. This is one of those moments where common language starts to wobble again. When people say the universe is expanding, it is natural to imagine matter rushing outward into surrounding nothingness. But general relativity does not require any outer container. Space-time itself changes. The emptiness between galaxies is not a passive gap being crossed. It is part of the dynamical system. Modern observations have made all of this far more than a beautiful mathematical idea. The bending of light by gravity, called gravitational lensing, is observed across the cosmos. Light from distant galaxies can be warped by the curved space-time around massive clusters, producing arcs, distortions, and multiple images. Time itself runs at different rates in different gravitational environments, something that must be accounted for in the global positioning system if accurate navigation is to work. Even satellites need Einstein. which is a mildly inconvenient truth for anyone hoping relativity was just an elegant academic hobby. Then there are gravitational waves. These are ripples in space-time produced by accelerating masses, especially violent events such as merging black holes or neutron stars. In 2016, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, announced the first direct detection of gravitational waves, confirming a major prediction of general relativity. Later observations by LIGO, Virgo and Kagra strengthened the result and opened an entirely new way of studying the universe. This was not matter shaking in space like a bell. It was space-time itself rippling. The European Space Agency has also played a major role in probing the structure of the cosmos, from precision cosmology to gravitational studies and future missions designed to detect space-time phenomena with even greater sensitivity. These institutions matter because they show that curved space-time is not philosophical ornament. It is measurable, testable, and woven into the most advanced observational science on Earth. All of this changes the meaning of vacuum before quantum theory has even fully entered the story. A vacuum in relativity is not simply a featureless blank where nothing happens. It can still have geometry. It can still allow waves in the structure of space-time itself. It can still expand, curve, and influence the motion of matter and light. In other words, even with very little matter present, the universe does not reduce to inert emptiness. The background has become physical. That is the key transformation. Classical intuition imagined empty space as a quiet container. Relativity turns it into an active participant. The emptier regions of the universe are no longer necessarily simple. They may be calm in one sense, but they are not devoid of structure. They may contain little matter, yet still possess shape, behavior, and measurable consequences. And yet, remarkable as that is, relativity still leaves room for an even deeper surprise. It gives space and time flexibility, geometry, and dynamical behavior, but it does not by itself say that the vacuum must be restless at the smallest scales. For that, physics must take another step. Once quantum theory enters the picture, the calmest possible state of empty space will begin to look less like stillness and more like a carefully hidden kind of activity. By the early 20th century, physics had already learned that empty space was more complicated than common sense first suggested. It was not simply a blank gap between objects. It could host fields, it could possess geometry, and under relativity it could even bend, stretch, and ripple. That alone was enough to disturb the old image of emptiness as a quiet, featureless background. But then a deeper problem emerged. The small-scale world refused to behave like a tidy little version of the large one. That refusal became the beginning of quantum physics. In classical thinking, nature is often imagined as a kind of perfect machine. Give the position and motion of every part, and in principle, the future can be calculated exactly. A planet moves in a predictable orbit. A thrown stone follows a smooth curve. A pendulum swings back and forth in a regular rhythm. There may be practical limits to prediction, but the underlying picture remains clear. The world is assumed to possess definite properties at all times, whether anyone measures them or not. That way of thinking worked beautifully for many familiar phenomena, but it began to crack when physicists looked closely at atoms, light, and energy itself. Max Planck played a crucial role in opening that crack. In 1900, while studying the radiation emitted by hot objects, Planck found that energy could not be treated as perfectly continuous in the way classical physics expected. To make sense of the observed spectrum of black body radiation, he introduced the idea that energy is exchanged in discrete packets, later called quanta. Planck did not set out to invent a revolution. Like many scientists standing at the edge of one, he was initially trying to repair an existing theory. But the repair changed the whole building. Soon after, Albert Einstein extended the quantum idea by showing that light itself could behave as if it came in packets of energy, now called photons. That helped explain the photoelectric effect and made it increasingly difficult to think of light as only a smooth classical wave. Then came Niels Bohr, who applied quantum ideas to the atom and proposed that electrons occupy specific allowed energy levels, rather than drifting freely in any orbit they pleased. The atom, once imagined as a miniature solar system, began to look less like a neat mechanical model and more like something governed by unfamiliar rules. This was the great conceptual turn. Nature at small scales did not behave like a tiny clockwork machine hidden inside matter. It behaved in ways that resisted direct visualization. The old intuition, shaped by balls, gears, trajectories, and continuous motion, started to fail. The deeper physics looked, the less obedient reality became to ordinary expectations. Werner Heisenberg sharpened this new picture with the uncertainty principle. This principle is often described casually and sometimes badly, so it is worth stating carefully. It does not mean that measuring instruments are merely clumsy, nor does it mean that the universe is vague because people have not tried hard enough. It means that certain pairs of physical quantities, such as position and momentum, cannot both be specified with unlimited precision at the same time. The more precisely one is defined, the less precisely the other can be fixed. That is not a statement about poor laboratory technique. It is a statement about the structure of quantum reality. A useful comparison is to imagine trying to pin down both exactly where a wave is and exactly what pure rhythm it carries. A perfectly localized splash is not a single clean frequency. A perfectly pure tone is not confined to one sharp instant. Quantum systems carry something of that same logic. They are not tiny hidden marbles waiting patiently to reveal exact classical properties once the right apparatus arrives. Their possible states are constrained by quantum laws from the beginning. Erwin Schrödinger gave this strange world one of its most powerful mathematical descriptions through wave mechanics. His work showed how quantum states evolve, and how particles such as electrons are better understood through wave functions than through neat little planetary orbits. The mathematics was successful, but the picture it offered was unsettling. Quantum entities did not simply sit in place and move along crisp paths in the way classical imagination preferred. They existed in states that had to be described probabilistically, with measurement playing a central role in what could be said about them. Taken together, the work of Planck, Bohr, Heisenberg, Schrödinger and others did more than change atomic physics. It changed what a lowest energy state could mean. That matters enormously for the story of empty space. In classical physics, the calmest possible state is easy to imagine. Everything stops, motion ceases, nothing wiggles, nothing fluctuates, nothing carries hidden ambiguity. A perfect vacuum, under that kind of intuition, ought to be completely still. It should be the physical equivalent of a room after every last sound has faded away, and even the dust has politely decided to remain motionless. Quantum theory does not allow that picture to survive intact. If position and momentum cannot both be fixed exactly, and if physical systems obey uncertainty at a fundamental level, then a state of exact perfect rest becomes much harder to define. At the quantum scale, complete stillness is not simply difficult to achieve. In many cases, it is not a meaningful physical possibility. A system can have a lowest energy state, certainly, but that lowest state does not automatically mean zero motion in the old classical sense. It does not mean a silent blankness stripped of every trace of activity. This is one of the most important shifts in the whole subject. Relativity had already taught that space is not a passive container. It has geometry, structure, and dynamical behavior. Quantum theory adds something even more quietly disruptive. It suggests that the calmest possible physical state may still contain irreducible restlessness, not noise in the ordinary everyday sense and not chaos for dramatic effect, but a built-in refusal of absolute stillness. That idea can feel slippery at first because classical instinct keeps trying to drag thought back toward familiar images. A system at minimum energy sounds as though it should be dead still. A vacuum sounds as though it should be inert. Empty space sounds as though it should behave like an erased blackboard. But the quantum world is under no obligation to preserve those expectations. At very small scales, the rules change, and once the rules change, the meaning of emptiness changes with them. So the quantum turn did not merely add new facts to physics, it altered the grammar of reality. It changed what could be known precisely, what could be predicted in the old way, and what the word empty could possibly mean when pushed to its deepest limit. The older image of vacuum as a quiet blank had already been weakened by fields and relativity. Quantum theory now begins to show why that image may fail completely. Even where nothing obvious is present, the laws themselves may forbid perfect stillness. And once that possibility is taken seriously, empty space starts to look less like absence and more like a state with hidden rules waiting to be uncovered. Quantum mechanics had already done enough to make the small-scale world feel unfamiliar. It had unsettled the old certainty that nature behaves like a miniature clockwork device. It had introduced uncertainty, probability, and a deeper limit on how sharply certain properties can be defined at once. But even then, there was still a lingering habit of thought that pictured particles as the basic ingredients of reality. Tiny objects, perhaps strange ones, perhaps not fully classical, but still objects first. Little bits of matter, little packets of light, little things moving through space. Quantum field theory changed that picture in a much deeper way. In this framework, the most fundamental ingredients are not particles in the ordinary sense. They are fields. These fields are not confined to one corner of the universe or tucked away inside matter. They extend throughout space. The electron field is everywhere. The photon field is everywhere. The quark fields are everywhere. The Higgs field is everywhere. What is usually called a particle is not the underlying substance itself, but a local excitation of one of these fields. In other words, an electron is not best understood as a tiny solid bead drifting through emptiness. It is a quantized excitation of the electron field. A photon is a quantized excitation of the electromagnetic field. That shift is easy to say and much harder to absorb. It asks the mind to stop treating space as an empty container with things placed inside it, and to start treating reality as a set of continuous fields spread across the whole of space-time. The things that appear to be separate particles are then the visible, measurable events that arise when those fields are excited in particular ways. A useful comparison, though only a comparison, is to think of waves on the surface of a sea. The wave is real. It has energy, motion, and consequences. It can travel, interact, and be observed. But it is not separate from the water beneath it. In much the same spirit, a particle is a detectable event in a field, not necessarily a tiny self-contained object sitting beneath all theory like a secret marble. This is one of the reasons the idea of empty space begins to change so dramatically. If fields exist throughout space, then a region without particles is not automatically a region without physical reality. It may simply be a region in which the fields are in their lowest energy states. That is a very different image from the older one. Emptiness is no longer the absence of everything. It becomes a condition of the fields themselves. The path toward this picture was not instant, and it was not the work of one person. Paul Dirac played a crucial role in the early synthesis of quantum mechanics with special relativity. Dirac's equation for the electron, developed in the late 1920s, did something extraordinary. It described electron behavior in a way consistent with relativity, and also predicted the existence of antimatter, specifically the positron, before it was observed experimentally. That alone would have secured Dirac a place in the history of physics, but his broader importance here lies in how his work opened the door to a field-based understanding of quantum particles. Once relativity and quantum theory were both taken seriously, the older pictures began to strain. A world of fixed particle numbers became difficult to preserve. At high enough energies, particles could be created and destroyed, matter could become radiation, and radiation could produce matter, provided the relevant conservation laws were satisfied. This was not a side note. It meant that a theory based on a fixed set of little objects moving around like celestial dust was too limited. Physics needed a deeper language, one in which the creation and destruction of particles could be handled naturally. That language became quantum field theory. Richard Feynman, Julian Schwinger, and Shinichiro Tominaga were among the key architects of the modern form of this theory, particularly in the development of quantum electrodynamics. Quantum electrodynamics is the quantum field theory of the electromagnetic interaction, describing how charged particles such as electrons interact through the electromagnetic field. It remains one of the most precise theories ever constructed. Its predictions and experimental measurements agree to astonishing accuracy in cases such as the electron's magnetic moment. When physicists say a theory works extremely well, this is one of the gold standards they have in mind. Feynman is especially well known because of his diagrams, which provide a powerful way to represent interactions in quantum field theory. These diagrams are often shown as if particles are exchanging other particles in simple little meetings, and that is a useful computational shorthand. But the deeper reality is field-based. The diagrams help calculate probabilities and interactions. They are not cartoons of tiny billiard balls passing handwritten notes. Useful though they are, they should not lure thought back into a purely particle-first picture. The field remains the deeper structure. Schwinger and Tominaga, along with Feynman, helped solve major problems in the early theory through the development of renormalization, a method for handling infinities that appeared in calculations. The details are mathematically demanding, but the broader point is clear enough. Quantum field theory was not merely a philosophical preference. It became the framework through which modern particle physics could actually function and make accurate predictions. This matters because it changes what the vacuum is. In the older intuitive picture, a vacuum is simply a gap, a hollow, a place where the contents have been removed. In a field-based picture, vacuum means something far more specific. It is the lowest energy state of the relevant quantum fields, not a place outside the fields, not a hole where fields have vanished. The fields remain present. What changes is their state. That may be the central idea of the whole subject. Empty space is not really empty because the basic ingredients of reality are not little objects sprinkled through a void. They are fields that pervade space. Even where no particles are present, the fields are still there. A vacuum is therefore not nothing. It is the ground state of something. This is why the earlier discussion of quantum uncertainty matters so much. Once the fields themselves are quantum in nature, the uncertainty principle no longer applies only to particles imagined inside space. It applies to the fields that constitute the deep structure of space. Quantum mechanics had already suggested that exact classical stillness may be impossible in many systems. Quantum field theory now carries that lesson directly into the vacuum. The background is no longer just the place where events occur, it is part of the physical content of the theory. A modern particle detector helps make this concrete. When a detector registers an electron, it is not thought of as having discovered a previously hidden pebble tucked into a corner of the universe. It has detected an excitation of the electron field. When it records a photon, it has registered an excitation of the electromagnetic field. The field is primary. The particle is the measurable manifestation. The event is local, but the underlying field is not. This also helps explain why different kinds of particles exist at all. Electrons are all identical, because they are excitations of the same electron field. Photons are identical, because they are excitations of the same electromagnetic field. The sameness is not a coincidence or a manufacturing success story on nature's part. It follows from the field structure itself. Nature is not handcrafting each electron one by one with remarkable quality control. It has chosen the more efficient route of producing one field and letting its excitations repeat. Once that picture settles in, the meaning of empty space cannot return to its older simplicity. A region without atoms is not a region without the electron field. A region without light is not a region without the electromagnetic field. A region without visible particles is not a region outside physical law or beyond physical structure. It is a region in which the fields may be quiet in a specific technical sense, but not absent, and that quietness is exactly where the next layer of strangeness begins. Because if the vacuum is the lowest energy state of quantum fields, then the natural question is no longer whether empty space contains anything at all. It becomes a subtler and more interesting question. What is the lowest energy state of a quantum field actually like? Is it perfectly still, as classical instinct would prefer? Or does the quantum nature of the fields ensure that even their calmest possible condition contains some irreducible activity hidden beneath the surface? By this point, the word vacuum has moved a very long way from its everyday meaning. It no longer means a blank place, a hollow region, or a simple absence of stuff. In modern physics, vacuum has a much stricter meaning. It is the lowest energy state of a set of quantum fields. That definition sounds technical because it is technical, and in this case the technical meaning matters more than the ordinary one. The shift is subtle at first, but once it settles in, it changes the whole subject. A vacuum is not defined by the complete non-existence of reality. It is defined by the state of the fields that underlie reality. If the electron field, the electromagnetic field, and other quantum fields are all in their lowest available energy states, then that condition is called vacuum. Not because nothing exists there, but because nothing has been excited into what would be recognized as ordinary particles. That is an extremely different picture from the older idea of empty space. In the older intuition, emptiness means contents removed. In the modern physical picture, vacuum means fields unexcited, or more carefully, in their ground states. The distinction matters because a ground state is still a state. It has properties. It can be described mathematically. It can influence what happens in that region. It can even differ from one theoretical situation to another. A useful comparison is a musical instrument at rest. A violin resting on a table is not producing a note, but it still exists as a physical system with strings, tension, and possible modes of vibration. Silence does not mean the instrument has vanished. In a somewhat similar way, a quantum field in its vacuum state is not absent. It is simply not excited into the kind of activity that registers as a particle detection. The field remains part of the structure of the world. This is where the phrase lowest energy state becomes especially important. In everyday language, low energy often suggests near total inactivity. A room at the end of a dull meeting may be described that way. In classical physics, that instinct often works well enough. If a system loses energy, it tends to settle down. Motion reduces, oscillations weaken, things approach stillness. So it is tempting to assume that the lowest energy state of a field should mean complete and perfect quiet. Quantum theory does not allow that assumption to survive unchanged. A lowest energy state is not the same thing as zero existence, and it is not always the same thing as absolute stillness in the classical sense. A quantum field can be in its ground state and still possess non-trivial properties. That sentence may not sound dramatic, but it is one of the most important ideas in the entire story. The vacuum is not a hole in reality. It is the baseline condition of something real. This is also why different fields can have different vacuum properties. The vacuum is not one simple universal emptiness in the way ordinary language might suggest. In physics, the details depend on the theory and on the field in question. The electromagnetic field has a vacuum state. The electron field has a vacuum state. The Higgs field has a vacuum expectation value, which means that even in what is called vacuum, the Higgs field does not simply sit at zero in the naive everyday sense. Instead, it has a non-zero background value throughout space. That fact is not decorative. It is central to how certain particles acquire mass within the standard model of particle physics. This alone is enough to show that vacuum is not a poetic synonym for nothingness. It is a technical condition defined within quantum field theory, and the details matter enormously. A field can be present everywhere and yet be in vacuum. A vacuum can therefore contain structure without containing ordinary particles. Once that is understood, the phrase empty space starts to sound almost misleading, or at least incomplete. Modern particle physics treats this with complete seriousness. At institutions such as CERN, vacuum is not a mystical abstraction or a philosophical ornament. It is part of practical scientific language. The Large Hadron Collider operates with beam pipes maintained at extraordinarily low pressures, lower than the pressure on the lunar surface in some sections, because particle beams need to travel through regions with as little residual gas as possible. That engineering vacuum is not identical to the theoretical vacuum of quantum field theory, but the two ideas are closely related in scientific practice. One concerns the removal of ordinary matter from an apparatus. The other concerns the lowest energy state of the fields that remain fundamental, even when matter has been reduced away. That difference is worth holding on to carefully. A laboratory vacuum is an experimental achievement. A quantum vacuum is a theoretical and physical state. They are related but not interchangeable. A beam pipe at CERN can be emptied of most gas molecules, but the quantum fields do not leave out of politeness. They remain. The vacuum state remains. The physics remains. The same general language appears throughout high-energy physics, accelerator science, and theoretical work more broadly. Physicists do not speak about vacuum because it sounds dramatic. In truth, physicists are often trying very hard not to sound dramatic. They use the term because it is precise. It refers to a specific state of the fields, and once that state is defined, one can ask careful questions about its energy, its symmetry, its stability, and its observable effects. That is another reason why the vacuum cannot be reduced to a simple image of nothingness. It may possess symmetry or broken symmetry. It may have measurable consequences for particles moving through it. It may differ between models of the early universe and the present day. In certain theories, it may even be possible to speak of false vacuum states, meaning states that appear stable but are not the true lowest energy configuration. The vacuum, in other words, behaves less like emptiness and more like a physical condition with character. At this stage, the word empty begins to lose some of its authority. A region with no atoms may still contain fields. Those fields may still have a lowest energy configuration. That configuration may still matter for particle physics, cosmology, and the structure of the universe itself. So when modern physics refers to vacuum, it is not praising absence. It is identifying a baseline level of physical reality. And that baseline is not necessarily passive. Once vacuum is understood as a real state, rather than a mere gap, a more interesting question emerges. If the vacuum is the ground state of quantum fields, can it do anything? Can it influence particles? Can it affect energy levels? Can it produce observable consequences? Can its properties be probed rather than simply defined? Those questions pull the subject out of abstraction and into experiment. The vacuum stops being something physicists merely talk about and starts becoming something they can detect indirectly through its effects. That is where the subject becomes even more revealing. Because once the vacuum is treated as physically real, it becomes natural to ask whether it is perfectly calm or whether its quietness hides a deeper kind of motion. Not motion in the old mechanical sense, but quantum activity woven into the ground state itself. And if that activity exists, then empty space is not only structured, it is active in ways that can leave measurable traces across the physical world. Once the vacuum is treated as a real physical state, rather than a poetic absence, a difficult question appears almost immediately. What does the lowest possible energy state actually mean? In ordinary life, the phrase lowest energy sounds simple enough. A swinging pendulum eventually slows. A ringing bell fades. A rolling ball comes to rest. Energy drains away. Motion dies down. And the system settles into stillness. Classical intuition is built around that picture. If something has reached its minimum energy, then surely it has become completely quiet. Quantum physics does not grant that wish. In many quantum systems, the lowest possible energy state still contains some irreducible energy. This is called zero-point energy. The name sounds slightly austere, as though it belongs on a clipboard in a particularly strict laboratory. But the idea is surprisingly vivid once it is understood. 0-point energy is the residual energy that remains even when a quantum system has been brought as low as it can go. It is not excess energy waiting to be removed by better engineering. It is not a flaw in the apparatus. It is part of the system's most basic physical description. That is one of the crucial reasons empty space is not really empty. If the vacuum is the ground state of quantum fields, and if ground states can possess unavoidable residual energy, then emptiness is not just occasionally interrupted by interesting events. It is built on a condition that is never perfectly motionless to begin with. A simple route into this idea comes from one of the most famous models in quantum physics, the quantum harmonic oscillator. The name may sound forbidding, but the basic image is gentle enough. It is the quantum version of something like a mass on a spring, a system that can move back and forth around an equilibrium point. In classical physics, this is straightforward. The spring stretches, compresses, and oscillates. If all the energy is removed, the mass settles exactly at the equilibrium point and remains there, perfectly still. Quantum mechanics refuses to allow that exact stillness. The reason comes back to the uncertainty principle associated with Werner Heisenberg. If the oscillator were fixed exactly at its equilibrium point with exactly zero motion, then both its position and its momentum would be perfectly defined at once. Quantum mechanics does not permit that. The more tightly the position is pinned down, the less definite the momentum becomes, and vice versa. So the system cannot simply sit at the bottom in the perfectly frozen classical way. Its ground state must retain a minimum amount of unavoidable energy. That leftover energy is the 0-point energy. It helps to think of it not as a buzzing machine in the ordinary sense, but as a built-in refusal of absolute stillness. The system is as quiet as quantum law permits, but quantum law does not permit the total silence classical intuition expects. The ground state is calm, yes, but not dead. Stable, yes, but not perfectly empty of dynamical possibility. Nature, at this level, never quite switches itself fully off. This idea emerged naturally from the development of quantum theory, after Max Planck first introduced the quantization of energy. Planck's work on blackbody radiation helped establish that energy comes in discrete amounts under the right conditions. From there, the broader quantum framework developed through the work of Niels Bohr, Erwin Schrödinger, Werner Heisenberg, Paul Dirac, and many others. 0-point energy is not some fringe add-on attached later for drama. It is woven into standard quantum reasoning. It appears when the theory is applied consistently, especially in systems like the quantum harmonic oscillator that serve as foundational models across physics. That model matters far beyond springs and toy examples. In quantum field theory, fields can be understood as collections of many harmonic oscillator-like modes. Each allowed mode of a field behaves mathematically in a way closely related to an oscillator, and if each oscillator has a non-zero ground state energy, then the field itself inherits a kind of baseline energy even in vacuum. That is where the idea becomes especially powerful. The vacuum is not just empty space with all the furniture removed, it is the lowest energy configuration of fields that themselves cannot be reduced to perfect classical stillness. A useful comparison is to imagine trying to flatten the surface of a lake so completely that not even the tiniest ripple remains. In classical imagination, this sounds possible. Wait long enough, remove every disturbance, and the water becomes perfectly flat. In the quantum world, the equivalent hope runs into a limit. The surface may become calmer and calmer, but at the deepest level there remains an irreducible softness to the stillness, a built-in residual motion that does not come from outside disturbance, but from the rules of the system itself. The comparison is imperfect, but it captures the feeling of the thing. The stillness is real, just not absolute. This distinction matters because it changes the meaning of the ground state. The ground state is not nothing. It is not a blank entry in the ledger of reality. It is the most reduced physical condition available under the laws of quantum physics, and even that condition retains structure. Once this is accepted, empty space begins to look less like a void and more like a carefully restrained physical medium whose quietest form still contains irreducible energy. That does not mean the vacuum is a roaring sea of obvious motion in the everyday sense. It does not mean one could place a windmill in empty space and expect it to spin cheerfully on the energy of nothing. The history of bad ideas includes many attempts to turn vacuum energy into a kind of magical, infinite fuel source, and physics has been obliged to disappoint them. The point is subtler. 0-point energy tells us that the lowest state is not the same as a state of classical deadness. The vacuum has a baseline condition that is physically meaningful, whether or not it can be harvested for science fiction convenience. Different areas of physics reveal this in different ways. In atomic systems, 0-point motion plays a role in how particles behave even at extremely low temperatures. In condensed matter physics, it helps explain why certain systems do not simply freeze into classical immobility. In quantum field theory, it becomes part of the conceptual foundation for understanding vacuum effects. The idea is broad, standard, and deeply embedded in modern science. This is why the subject reaches beyond technical language and touches the title directly. Empty space is not really empty, not only because particles can sometimes appear in useful descriptions, and not only because fields are present throughout space, but because the quietest possible state of those fields is already not perfectly still. The emptiness is structured from the bottom up by ground states that retain unavoidable residual energy. The absence is not absolute. The silence has a floor beneath it, and that floor is not zero in the naive classical sense. Once that becomes clear, a great deal else begins to make more sense. If the vacuum contains irreducible energy, then it is less surprising that it can influence the behavior of matter. It is less surprising that particles interacting with fields may register subtle shifts in energy. It is less surprising that empty space can leave experimental fingerprints rather than merely standing there looking innocent. And it also prepares the ground for a more delicate idea. If the vacuum state is not perfectly inert, then perhaps it is not merely a passive baseline. Perhaps it can exhibit fluctuations. Perhaps its residual quantum character can produce transient effects that alter what happens to particles, atoms, and forces. Once the lowest energy state is understood as physically real and permanently a little restless, the next step is no longer hard to imagine. The vacuum does not need to be full of obvious objects to matter. It only needs to be active enough, in its own quiet quantum way, to leave traces behind. By now, empty space has already lost most of its old innocence. It is no longer a simple blank. It contains quantum fields, and those fields possess ground states that are not perfectly still. That much is already enough to make the vacuum physically real. But the next idea is where the subject often becomes both fascinating and badly mangled at the same time. This is the territory of vacuum fluctuations. Vacuum fluctuations are changes associated with the quantum state of fields, especially with the fact that the vacuum is not a classically fixed and silent condition. The phrase points to the restless character of the quantum vacuum, to the idea that even in its ground state, a field is not identical to a frozen classical zero. There is irreducible quantum structure there. There are correlations, uncertainties, and effects that can influence measurable phenomena. That is the careful version. The popular version is usually shorter and more dramatic. Particles pop in and out of existence. Space bubbles with ghostly matter. Tiny things appear, vanish, borrow energy, and sneak away before the universe notices. It is vivid language. It survives because it gives the imagination something to hold on to. And to be fair, it is not entirely useless. It gestures toward a real truth, which is that the quantum vacuum is not empty in the classical sense, and that field theory does allow processes that are not well described by a calm, static picture of nothingness. But the phrase also causes trouble, because it invites the mind to picture literal tiny objects flickering into being like fireflies in the dark, briefly stealing energy from the cosmic bank before a stern accountant arrives. The universe, despite appearances, is not usually run like a badly supervised corner shop, so it is worth slowing down and separating what the phrase gets right from what it gets wrong. What it gets right is the central fact that the vacuum in quantum field theory is active in a meaningful sense. The vacuum is a state of fields, and those fields have quantum uncertainties and non-trivial correlations even in their ground state. Calculations in quantum electrodynamics and other field theories show that vacuum effects contribute to real physical outcomes. The vacuum is not just an empty stage with no role in the performance. It participates in the theory and helps shape what is observed. What the phrase gets wrong is the image of ordinary particles as tiny self-contained marbles, literally appearing from absolute nothing, existing for a moment, and then vanishing again in a straightforward visual sense. In rigorous physics, this picture is much too naive. The language of particles in these contexts is often tied to perturbation theory, to field excitations, to internal lines in Feynman diagrams, and to calculational structures that should not always be read as miniature historical events occurring exactly as drawn. Richard Feynman is especially relevant here because his diagrammatic approach became one of the most powerful tools in modern quantum field theory. Feynman diagrams are wonderfully useful. They allow physicists to organize and calculate interaction probabilities in quantum electrodynamics and beyond. An electron emits a photon. A photon couples to charged particles. Loops appear in the calculation, representing contributions from more complicated internal processes. These diagrams are elegant, efficient, and deeply important. But they are not simple snapshots of tiny objects marching through space in the ordinary literal sense. They are pieces of a mathematical expansion. They encode terms in an amplitude. They help calculate what is observed when quantum fields interact. If one stares at them too literally, confusion arrives very quickly. This is where so-called virtual particles enter the story. Virtual particles are often described as the things that pop in and out of existence in the vacuum. That description is catchy, but it is not the safest one. Virtual particles are not particles in the same sense as those directly detected in a laboratory. They do not obey the same on-shell relation that real observed particles do. They appear as internal elements in perturbative calculations, and their role is tied to the mathematical structure of the theory, rather than to a simple little hidden drama taking place beneath every event. They are useful. They are meaningful within the formalism. But they are not best imagined as tiny secret creatures dashing in and out of reality like nervous stagehands. A more careful way to think about vacuum fluctuations is this. The vacuum state of a quantum field contains irreducible quantum uncertainty and structure. Because of that, interactions with particles and with boundaries can reveal measurable consequences that would not arise if space were a truly classical blank. The language of fluctuating particles is one way of talking about that, especially in perturbative contexts, but it is not the most fundamental statement. The deeper statement is about the behavior of quantum fields and the properties of their ground states. This distinction may seem fussy, but it matters. Physics often reaches a point where the wrong picture is easier to imagine than the right one. The wrong picture can still lead to the correct emotional response, which in this case is wonder, but it can also smuggle in confusion. And once confusion settles in, the vacuum starts being described as magic rather than as physics. Then come the claims about limitless free energy, mystical manifestation, or the universe endlessly generating matter from pure nothing in a simple literal way. At that point, the science begins to slip. The more accurate story is still strange enough without the embellishment. Quantum fields do not allow the vacuum to be a perfectly inert classical zero. Their ground state contains non-trivial structure. Calculations reveal that this structure affects observable quantities. In that sense, the vacuum is active. It is not active in the way a storm is active or a machine is active. Its restlessness is subtler. It lives in probabilities, correlations, and the field-theoretic description of interactions. A useful comparison is to think of a perfectly still-looking surface that, on closer inspection, is not actually dead flat but carries microscopic tremors built into its nature. From a distance it appears calm. Under sufficient magnification, that calmness has texture. The quantum vacuum is something like that, though even this image should be handled gently. The point is not that space visibly froths with tiny balls. It is that the ground state is structured enough that certain effects arise inevitably from the theory. This is why physicists use the language carefully. In some settings, saying that particles pop in and out of existence is a quick informal shorthand. It points beginners toward the fact that the vacuum is not empty. But when precision matters, the shorthand has to be unpacked. What is really being described are field-theoretic contributions, quantum uncertainties, and the consequences of a vacuum state that is not classically trivial. And yet the wonder remains, perhaps even more so once the exaggeration is stripped away. There is something more impressive about a reality that is strange for exact reasons than a reality made strange by sloppy storytelling. The vacuum does not need fantasy added to it. It is already peculiar enough that the best theories in science insist that emptiness possesses hidden activity, and precise enough that this activity can influence measurable outcomes. That last point is where the subject becomes especially satisfying. If vacuum fluctuations are more than a poetic phrase, if they are tied to the genuine quantum structure of fields, then their effect should not remain forever locked inside theory. They should, at least in principle, leave traces. They should shift energies, alter forces, influence atomic behavior, or otherwise reveal themselves through experiment. Once the vacuum is understood as physically active in this careful sense, the next question becomes irresistible. Can any of that hidden restlessness be detected in the world, not merely talked about in equations, but measured in a way that shows empty space is doing something real? One of the most satisfying moments in this whole subject arrives when the vacuum stops being merely an idea and starts behaving like something that can be measured. Up to this point, empty space has become steadily less empty in theory. Fields exist everywhere. Their ground states are not perfectly still. Quantum fluctuations are part of the modern description. All of that is fascinating, but it can still feel slightly abstract, as though the vacuum is being given an impressive resume without ever being asked to prove it. The Casimir effect is one of the places where the vacuum begins to prove it. The basic idea is elegant. In 1948, the Dutch physicist Hendrik Casimir predicted that two very closely spaced conducting plates should experience a small attractive force not because of an ordinary spring, glue, or static cling in the everyday sense, but because of the way quantum fields behave in the space between them. That is the striking part. The geometry itself changes the vacuum. To see why this matters, it helps to imagine that the vacuum is not a featureless blank, but a state in which quantum fields can support different patterns, sometimes called modes. A mode is a permitted pattern of oscillation or excitation. The word may sound technical, but the idea is familiar in spirit. A guitar string can vibrate only in certain standing wave patterns if its ends are fixed. A flute supports certain resonant air patterns depending on its length and shape. The system does not allow just any wave whatsoever. The boundaries matter. Something similar happens with quantum fields near conducting plates. The presence of the plates imposes boundary conditions. That phrase simply means the field must satisfy certain rules at the surfaces of the plates. Because of those constraints, not every possible field mode is allowed in the narrow gap between the plates. Outside the plates, the field has a wider range of allowed modes. Inside the gap, the possibilities are more restricted. That difference changes the vacuum energy associated with the region between the plates compared with the region outside them. The result is a tiny net force pushing the plates together. In plain language, the vacuum between the plates is not identical to the vacuum outside them, because geometry and boundary conditions have modified what the field can do. The emptiness has been shaped. This is one of the clearest signs that the vacuum is not just a poetic idea. If empty space were truly a classical nothing, putting two plates near each other would not give the vacuum any opportunity to express an opinion. Yet in quantum field theory, it does. Constrain the allowed modes, and the physical situation changes. The vacuum responds to geometry. The force is extremely small, which is only polite of it. If empty space started slamming together every pair of metal surfaces in the kitchen, daily life would become exhausting. But at microscopic separations, the Casimir effect becomes measurable. For plates separated by distances on the order of tens to hundreds of nanometers, the force can be significant enough for precision experiments to detect. A nanometer for scale is 1/1000th of a meter, so this is very much a small distance story. The vacuum is subtle but not silent. The original idealized calculation involved perfectly conducting parallel plates, which is mathematically neat and physically instructive. Real experiments are less tidy because actual materials are not perfect conductors, surfaces are not perfectly smooth, temperatures are not always negligible, and alignment at nanometer scales is no one's idea of a relaxing afternoon. Even so, the effect has been measured in increasingly refined ways over the decades. Experimental physicists have observed forces consistent with Casimir-type predictions using plate and sphere arrangements, micro-electromechanical systems, and other delicate setups designed to separate the genuine signal from all the nuisance effects nature cheerfully supplies for free. This matters enormously because it moves the discussion from theory to measurement. The vacuum is not just being described as active in principle. It is leaving a physical trace in the laboratory. Two objects can feel a force because the quantum fields around them are constrained differently by their geometry. That is a remarkable sentence. It means that what looks like empty space between the plates is doing something measurable. The National Institute of Standards and Technology, along with similar precision measurement environments around the world, has contributed to the broader scientific culture in which effects like this are studied with care. Casimir force measurements are part of a wider world of metrology, surface physics, nanotechnology, and quantum experiments, where tiny forces and tiny distances must be handled with extraordinary precision. This is not the territory of vague wonder. It is the territory of careful calibration, controlled surfaces, temperature corrections, and researchers staring very hard at apparatus that most people would mistake for a small metallic inconvenience. There is also an important conceptual lesson here. The Casimir effect does not require the vacuum to be filled with literal tiny particles bouncing around like microscopic gnats. What matters is that the quantum field has allowed modes, that the plates restrict those modes, and that the difference in vacuum structure leads to a force. This is a good example of why careful language is useful. It shows the vacuum behaving physically without forcing the explanation into oversimplified imagery. It also teaches something deeper about emptiness itself. Empty space is not only something that can contain fields, it is something whose physical behavior can be altered by constraints. Change the boundaries and the vacuum changes with them. That is a very long way from the old idea of nothing as simple absence. In modern physics, emptiness can have structure, energy, and sensitivity to shape. There is a quiet beauty in that. Put two plates near one another and in a sense they do not merely sit inside the vacuum. They reshape the possibilities available to the fields around them. The gap between them becomes a different physical environment from the wider space outside. The vacuum is no longer an inert background, but a participant whose state depends on circumstance. Of course, the Casimir effect is not the final word on vacuum physics, and physicists still debate the best way to interpret certain aspects of it. Some presentations emphasize vacuum energy differences directly, while others frame the effect more in terms of fluctuating charges and field interactions within quantum electrodynamics. But whichever language is chosen, the core message remains the same. The quantum vacuum is not operationally empty in the classical sense. It has measurable consequences. And that opens an even more intimate question. If the vacuum can influence forces between carefully arranged metal surfaces, then perhaps it can also affect smaller systems more directly. Perhaps it can shift the behavior of atoms. Perhaps it can alter energy levels, affect the emission of light, or leave its fingerprints inside matter itself. Once empty space has shown that it can push on metal from the shadows, it becomes very hard to believe that it politely stops there. The vacuum does not only reveal itself in carefully engineered gaps between metal plates, it also leaves traces inside the atom, in places where matter and light interact so delicately that even tiny corrections become meaningful. This is one of the most important developments in the whole story, because it shows that the so-called empty background is not merely an exotic effect for rare laboratory setups. It is part of the fine structure of ordinary physical reality. It reaches into atoms themselves. A good place to begin is with hydrogen, the simplest atom. Hydrogen contains one proton and one electron, which makes it wonderfully useful for physicists. Nature has kindly supplied a system simple enough to study deeply and strange enough to remain interesting for more than a century. If the universe had wanted to be especially annoying, it could have made even the hydrogen atom impossible to analyze cleanly. Instead, it gave science a manageable starting point. Not perfect simplicity, but close enough to be invaluable. Early quantum theory, and later the Dirac equation, described hydrogen with impressive success. The allowed energy levels of the electron could be calculated, and much of the atomic spectrum made sense. But as measurement improved, tiny discrepancies began to appear between the expected energy levels and the observed ones. These were not large failures. The theory was not collapsing in disgrace. The problem was subtler and in a way more exciting. The atom was agreeing with theory almost completely, except for very small differences that seemed to whisper that something had been left out. One of the most famous of those whispers became known as the Lamb shift. In the late 1940s, Willis Lamb and Robert Rutherford carried out an experiment on hydrogen that showed two energy levels, which earlier theory had predicted should be identical, were in fact slightly different. This was a major result. The difference was tiny, but tiny does not mean trivial. In atomic physics, a minute shift can reveal something profound about the underlying theory. The Lamb shift showed that the electron in hydrogen was not behaving as though it lived in a perfectly clean static Coulomb field around the proton. Something more was going on. That something turned out to be deeply connected to quantum electrodynamics, the quantum field theory of light and charged particles. In this framework, the electron is not an isolated little object orbiting peacefully through empty nothing. It interacts with the electromagnetic field, and that field has a non-trivial vacuum state. The electron is influenced by the quantum structure of the vacuum around it. These vacuum effects slightly modify the energy levels of the atom. A simple way to picture the situation is to imagine that the electron does not move through a perfectly blank backdrop. Instead, it exists in an environment shaped by quantum fields, an environment that can subtly shift the rules of its behavior. The Lamb shift is one of the experimental signs of that deeper environment. The vacuum is not directly seen, but its influence is measured through the altered energy structure of hydrogen. This was one of the triumphs of quantum electrodynamics. The theory developed by Richard Feynman, Julian Schwinger, and Sinnatira Tomonaga, building on earlier foundations from Paul Dirac and others, was able to account for the Lamb shift with extraordinary success. It showed that the tiny discrepancy was not an embarrassing flaw but a clue. The clue pointed toward a richer picture of the atom, one in which vacuum effects, self-interactions, and quantum corrections all matter. That is the broader lesson here. The atom is not a sealed mechanical toy. It is embedded in a field-theoretic universe. Even in what might casually be called empty space, the electron is not alone with the proton. The quantum vacuum is part of the situation. Another striking example is spontaneous emission. This is the process by which an excited atom emits a photon and drops to a lower energy state. At first glance, that may sound perfectly ordinary. Atoms absorb and emit light all the time. But once the question is asked carefully, something remarkable appears. Why does the excited atom emit at all when left alone? What prompts the transition? In a classical picture, one might imagine that something external must trigger the atom. A push, a disturbance, a passing wave, some visible influence. But in quantum electrodynamics, the electromagnetic vacuum itself provides the necessary background structure. Even when no real photons are present in the everyday detectable sense, the vacuum state of the field is not trivial. The atom is coupled to that field, and the interaction allows spontaneous emission to occur. This is another way the vacuum reveals itself. It does not merely alter special forces between plates, it helps govern whether and how atoms emit light. The darkness around an atom is not classically empty. It is the vacuum state of the electromagnetic field, and that state matters. There has long been some nuance in how physicists describe spontaneous emission. One can frame it in terms of vacuum fluctuations stimulating the emission, or in terms of radiation reaction, where the charged particle interacts with its own emitted field. In the full theory, these descriptions are related, and the deeper message remains the same. A purely classical blank background is not enough. The quantum field environment is part of the explanation. This is where the evidence becomes especially persuasive. The vacuum is not just something that affects carefully arranged conductors at nanometer distances. It is woven into the fine detail of atomic behavior. Hydrogen, the simplest atom, carries its imprint. Light emission, one of the most familiar processes in nature, carries its imprint. The so-called empty background is participating in ordinary microscopic reality. Historically, this work belonged to a broader world of precision measurement. Institutions such as the United States National Bureau of Standards, later renamed the National Institute of Standards and Technology, along with university spectroscopy groups and atomic physics laboratories around the world, helped create the culture of exact measurement in which tiny shifts could be discovered and trusted. The Lamb shift was not a grand theatrical effect. It was a subtle difference found by careful experiment and interpreted through a theory of remarkable depth. That subtlety is part of its power. When empty space influences a metal apparatus, the result is impressive. When it influences the energy levels of hydrogen, the message becomes even harder to ignore. The vacuum is not a remote abstraction, it is embedded in matter itself. There is also a pleasing consistency here. The Casimir effect showed that the vacuum can respond to boundaries and geometry. Atomic physics now shows that the vacuum can also affect the internal energy structure of matter and the emission of radiation. The evidence base widens. Empty space is not only conceptually active and not only experimentally consequential in special setups. It is part of a wider pattern in which the quantum vacuum helps shape measurable outcomes across the small-scale world. And once that is admitted, the picture of particles becomes more interesting too. If atoms are influenced by the vacuum, then particles cannot really be treated as isolated little things moving through a dead background. They are immersed in fields dressed by interactions and shaped by the deeper structure around them. The vacuum does not merely sit behind reality. It helps form the conditions under which reality appears at all. By now, the old image of particles as tiny self-contained objects has become harder and harder to maintain. The evidence does not quite let them stay simple. Electrons are influenced by the vacuum. Atoms do not emit light as though they live in a dead background. The Casimir effect shows that geometry can alter the vacuum itself. Piece by piece, the picture changes. What looks like isolated matter begins to resemble local behavior taking place within a deeper sea of fields. This is one of the most important changes in perspective modern physics asks of anyone trying to understand the small-scale world. A photon is not best imagined as a little glowing pellet flying through emptiness. An electron is not best imagined as a tiny grain wandering through a blank void. Those pictures are sometimes useful in rough everyday explanation, but at a deeper level they are incomplete. In quantum field theory, photons, electrons, quarks, and other particles are excitations of underlying fields. They are localized events or disturbances in those fields, measurable and real, but not independent of the field structure that gives rise to them. That means particles do not sit on top of reality like beads scattered across a table. They arise from reality's deeper fabric. The table, so to speak, is already doing much of the work. A helpful way to think about this is to imagine the difference between a wave and the water beneath it. The wave has shape, direction, and energy. It can travel across the surface and interact with other waves. It is perfectly real. But it is not separate from the water. Remove the water and the wave is gone, because the wave is a behavior of the medium rather than an independent object hovering above it. Quantum fields are not water, and particles are not literally ocean waves, but the comparison captures the logic. What looks like a separate particle is, in the deeper theory, a specific kind of excitation of a field that extends throughout space. This matters because it changes how light and matter are understood. A photon is an excitation of the electromagnetic field. An electron is an excitation of the electron field. Quarks are excitations of quark fields. The Higgs boson is an excitation of the Higgs field. The particle is what the detector records, what the experiment measures, what the mathematics predicts as a quantist event. But the underlying physical language is field-based. That is the framework now built into the standard model of particle physics, the accepted theory describing the electromagnetic, weak and strong interactions among the known fundamental particles. The standard model is not a complete theory of everything. It does not include gravity in the same quantum way, and it leaves several major questions open. But within its domain, it works extraordinarily well. Experiments at CERN, including those carried out with the Large Hadron Collider, have tested its predictions to very high precision. The discovery of the Higgs boson in 2012 was one of its great confirmations, and throughout this framework, vacuum is not an afterthought. It is part of the stage on which particle physics unfolds, though by now stage may be too passive a word. The vacuum is better understood as the baseline state of the fields themselves. This is why particles are often said to be dressed by their interactions. A real electron is not simply a bare point with a fixed, isolated identity, untouched by its surroundings. In quantum electrodynamics, the electron interacts with the electromagnetic field and with the vacuum structure around it. That interaction affects measurable quantities such as its effective mass and magnetic properties. In this sense, the particle and the vacuum cannot be cleanly separated. The observed electron is the electron as it exists within a quantum field environment, not as an imagined object floating in perfect classical emptiness. The same general logic applies more broadly. Matter and radiation are inseparable from the fields beneath them, and those fields are inseparable from their vacuum states. The vacuum is not just where particles happen to be absent. It is the baseline condition against which particles are defined in the first place. This is where the language of virtual processes often appears, and it needs to be handled carefully. In perturbative quantum field theory, interactions are often described using terms that include intermediate processes represented in Feynman diagrams. These internal contributions are sometimes spoken of as virtual particles. That language is useful within calculation, and physicists continue to use it because it helps organize what the mathematics is doing. But it should not be confused with the image of a literal foam made of tiny hidden billiard balls darting around beneath reality like frantic office workers before a surprise inspection. Virtual processes are not best understood as miniature ordinary events happening in quite the same way real detected particles do. They are part of how the theory calculates amplitudes and interaction strengths. They represent contributions within the formalism, not necessarily little secret dramas unfolding exactly as drawn. This is an important distinction because once it is lost, the vacuum quickly gets misdescribed as a simple soup of invisible objects rather than as a quantum state of fields with non-trivial structure. Even so, the language points toward a genuine truth. Particles are not isolated from the vacuum. Interactions with quantum fields, including the vacuum state of those fields, affect what particles do and how they appear experimentally. The vacuum is not a blank backdrop behind light and matter. It is part of the same physical story. This more general worldview pulls together everything that has come so far. The Casimir effect showed that vacuum structure can influence forces between surfaces. The Lamb shift and spontaneous emission showed that vacuum structure affects atoms and light. Now the wider conclusion comes into view. These are not disconnected curiosities. They are signs of a single framework in which particles are local excitations living on top of deeper field behavior. Once that framework is accepted, the universe starts to look different. A beam of light crossing space is not simply a thing moving through nothing. An electron in an atom is not simply a particle sitting in a tiny mechanical orbit. Matter, radiation, and vacuum belong to one interconnected field picture. The so-called empty regions of the universe are not outside the theory. They are part of its most fundamental content. There is something both elegant and slightly humbling about that. Human intuition prefers distinct objects and clean gaps between them. Physics, when pushed deeper, often offers something less familiar and more continuous. The objects remain real enough to measure, real enough to detect, real enough to build technologies from. But beneath them lies a world in which fields are primary, vacuum states matter, and separation is not always as sharp as it first appears. And once particles and vacuum are understood together in that way, a larger question begins to emerge. If the quantum vacuum helps shape matter and radiation at the smallest scales, then perhaps it did more than influence atoms and laboratory experiments. Perhaps its structure mattered in the early universe itself. Perhaps what looked like microscopic restlessness in empty space helped seed patterns on the largest scales of all, leaving traces not just in detectors and spectra, but across the architecture of the cosmos. The story now widens so dramatically that the scale almost becomes difficult to hold in the mind. The vacuum has already shown that it can influence atoms, forces, and small laboratory systems. But modern cosmology suggests that the restless character of empty space may have mattered on a far grander stage. It may have helped shape the visible universe itself. The central idea is both simple and extraordinary. In the very early universe, tiny quantum fluctuations may have existed in fields filling space. Under ordinary conditions, those fluctuations would remain microscopic, relevant to the small-scale world but not obviously to galaxies and clusters. But if the universe underwent a brief period of extremely rapid expansion, called cosmic inflation, then fluctuations that began on quantum scales could have been stretched to enormous sizes. What started as minute irregularities could later become the seeds from which large-scale structure grew. Inflation is a leading cosmological idea developed in important early forms by Alan Guth, and later expanded in influential ways by Andrei Linde and others. The basic proposal is that, in a very early fraction of a second, the universe expanded exponentially fast. Space itself swelled at a tremendous rate. This was not ordinary motion through pre-existing emptiness. It was the rapid expansion of spacetime. In that process, tiny differences in energy density could be stretched across vast distances. Those stretch fluctuations matter because gravity amplifies unevenness. A region that is slightly denser than average attracts a little more matter. Over immense spans of time, that slight advantage grows. Gas falls in. Structures form. Galaxies emerge. Clusters gather. The cosmic web develops. In this picture, the large-scale structure of the universe did not begin as a perfectly smooth expanse. It began with faint imprints, and those imprints may have had quantum origins. That possibility is one of the most astonishing links in modern science. The same quantum principles that govern atoms, photons, and vacuum behavior in laboratory physics may also have helped determine where galaxies eventually formed. The small scale and the cosmic scale are not separate stories stitched together afterward. They may be connected from the beginning. Evidence for this broader picture comes in part from the cosmic microwave background, the faint relic radiation left from the early universe. This radiation preserves a map of tiny temperature variations across the sky, differences at roughly the level of 1 part in 100,000. Those minute variations are not random clutter. They encode information about the early universe and the seeds of later structure. Missions led by NASA, the European Space Agency, and especially the Planck mission have measured these patterns with extraordinary precision. The results strongly support the idea that the early universe was nearly smooth, but not perfectly smooth, and that the pattern of those irregularities is consistent with what inflationary models can produce. That does not mean every detail is settled. Inflation remains a powerful and successful framework, but not every version of it is equally favoured, and important questions remain open about exactly what drove it, how it began, and whether it connects directly to a specific quantum field or vacuum state. Cosmology is rarely shy about leaving a few deep mysteries on the table. Still, the broad implication is difficult to ignore. Empty space, or more precisely the quantum fields in their early universe state, may have carried fluctuations that were stretched outward and frozen into the architecture of the cosmos. That means the vacuum is not merely a microscopic curiosity. It may have left fingerprints across the largest visible scales in existence. There is a certain quiet elegance in that possibility. A faint quantum tremor in the early universe, far smaller than any atom, may have helped determine where entire galaxies would later shine. The vast spiral systems seen by telescopes, the clusters spread across millions of light years, even the broad web-like arrangement of matter in the observable universe, may trace part of their ancestry to the restless behaviour of fields in what look like almost nothing. So the pattern is becoming harder to dismiss as a collection of special cases. The vacuum influences atomic energy levels. It alters forces between surfaces. It helps define particles through underlying fields. And if modern cosmology is even approximately right, it may also have provided the tiny seeds from which the visible universe grew. What first appeared to be a subtle oddity of quantum physics begins to look more like a deep feature of reality itself. The strange influence of empty space does not seem to end with atoms, laboratory forces, or the early universe. It may also reach into one of the largest and most unsettling discoveries in modern cosmology, the fact that the expansion of the universe is speeding up. For much of the 20th century, the central expectation was fairly straightforward. The universe had been expanding since the Big Bang, and gravity, acting across cosmic distances, ought to slow that expansion over time. Matter attracts matter. Galaxies pull on one another. Even if the universe never collapsed back in on itself, many physicists expected the expansion to decelerate gradually, like a ball thrown upward that continues rising but loses speed. Instead, observations in the late 1990s pointed towards something far stranger. Distant Type 1, a supernovae, used as standardizable candles to estimate cosmic distances, appeared dimmer than expected in a decelerating universe. The implication was remarkable. The expansion was not slowing down in the expected way, it was accelerating. Space itself was stretching faster over time on the largest scales. This result came from major observational efforts, including the Supernova Cosmology Project and the High Z Supernova Search Team. It has since been supported by other lines of evidence, including measurements of the cosmic microwave background, large-scale structure, baryon acoustic oscillations, and galaxy surveys. Observations from the Hubble Space Telescope, the Dark Energy Survey, and the European Space Agency have all contributed to the broader picture. The result is now part of the standard cosmological model, however strange it may still sound. The universe is expanding, and that expansion is accelerating. The name given to the unknown driver of this behaviour is dark energy. The name is honest in a slightly bleak scientific way. It tells what the effect does, not what it fundamentally is. It behaves as though some form of energy associated with space itself contributes a repulsive large-scale effect, one that becomes more important as the universe grows larger and matter becomes more diluted. Dark energy is not called dark because it is moody or stylish. It is called dark because its underlying nature is not yet understood directly. This is where the vacuum returns in a much deeper and more troubling role. Albert Einstein introduced the cosmological constant in general relativity as an additional term that could, in effect, influence the large-scale behaviour of spacetime. Historically, he introduced it for reasons tied to a static universe, an idea later abandoned once cosmic expansion became clear. But the mathematical possibility remained. A cosmological constant acts like an energy density built into space itself. one that does not thin out as the universe expands. In modern terms, that sounds very much like one possible description of dark energy, and that immediately raises a natural question. Could dark energy simply be vacuum energy? At first glance, this sounds almost elegant. The vacuum in quantum field theory is not empty. It possesses ground state structure and irreducible energy. General relativity allows energy to influence the geometry and expansion of spacetime. Put those two ideas together, and one is tempted to say that the vacuum energy of quantum fields might be driving the accelerated expansion of the universe. It is a beautiful thought, almost too beautiful, which in physics is often where the trouble begins. The trouble is that when physicists try to estimate the vacuum energy in a naive, straightforward way using quantum field theory, the result is absurdly larger than the dark energy density inferred from cosmological observations. Not a little larger, not awkwardly larger. Larger by an immense and embarrassing margin, often described as the worst theoretical prediction in physics. Depending on how the estimate is framed, the mismatch can be on the order of roughly 120 powers of 10. That is such a huge discrepancy that ordinary language starts to lose traction. It is not the kind of error one tidies up with a better constant or a slightly improved instrument. It is a sign that something profound is missing in the connection between quantum field theory and gravity, or in the understanding of vacuum energy, or possibly in both. This is often called the cosmological constant problem, or more dramatically, the vacuum catastrophe. The phrase catastrophe is deserved. Physics has two extraordinarily successful frameworks in this story. Quantum field theory works brilliantly for particle interactions. General relativity works brilliantly for gravity and cosmic geometry. Yet when vacuum energy from one is plugged into the other in the most obvious way, the result is wildly wrong. Empty space, which has already proven itself active and structured, now sits at the centre of one of the deepest unresolved tensions in theoretical physics. That is what makes this subject so important. Empty space is not merely strange in a decorative way. It may be entangled with the fate of the universe. It may help explain why the cosmos expanded the way it did in its earliest moments, and it may also be tied to why expansion is accelerating now. The vacuum, once imagined as simple absence, has become relevant at both ends of cosmic history, in the seeding of structure and in the long-term evolution of spacetime. Of course, caution is needed here. It is not yet established that dark energy is literally vacuum energy, in the most direct, simple sense. The cosmological constant remains the simplest successful fit to current data within the standard model of cosmology, but the deeper physical interpretation is still unsettled. There are alternative ideas involving dynamical fields, modified gravity, or other beyond standard model possibilities, though none has yet displaced the cosmological constant as the leading effective description. The data are strong. The explanation remains incomplete. There is something almost unsettlingly symmetrical about the situation. At the smaller scales, the vacuum refuses to be empty. At the larger scales, the universe behaves as though empty space itself contributes to cosmic expansion. The same concept that once seemed like a philosophical afterthought now appears in the laboratory, in atomic structure, in the growth of galaxies, and in the future of the cosmos. That leaves physics in an uncomfortable but fertile position. The vacuum is clearly not nothing. It has measurable consequences. It influences the real world. Yet its full gravitational meaning remains obscure. Empty space is active, but not fully understood. And that may be the most revealing fact of all. The more closely reality examines nothing, the more that nothing turns out to be one of the heaviest problems in science. Once the vacuum is understood as a real physical state rather than a poetic emptiness, a new question naturally appears. Is there only one such state? Or could there be more than one? And if there can be more than one, how certain is it that the universe currently rests in the deepest possible version of empty space? This is where physics becomes quietly unsettling. In ordinary life, an empty room is just an empty room. It does not secretly wonder whether it could become a more correct room at some later date. But in quantum field theory, the vacuum is not a simple absence. It is a state of fields, and states can have structure, stability, and energy. That means it becomes meaningful to ask whether the vacuum we inhabit is the true lowest energy state, or only a local minimum that appears stable for now. The key idea here is the false vacuum. A false vacuum is a vacuum state that is stable enough to persist, perhaps for an extremely long time, but is not the absolute lowest energy state available. A helpful comparison is a ball resting in a shallow valley, on a landscape of hills and dips. If the ball sits in a hollow, it may remain there indefinitely unless something disturbs it. From the ball's local point of view, it is at rest and everything seems settled. But somewhere beyond the nearby ridge there may be a deeper valley. In that case, the ball is not in the true lowest state. It is only in a metastable one. Metastable is an important word here. It means stable for practical purposes, at least potentially for immense lengths of time, but not absolutely guaranteed in the deepest sense. Physics uses this idea in many areas, from materials to phase transitions, but in quantum field theory it acquires a particularly profound significance. If the vacuum of the universe were metastable rather than truly stable, then what looks like the calm baseline of reality would actually be a temporary arrangement. That does not mean temporary on human timescales, or even on stellar timescales. In many theoretical discussions, the lifetime of such a metastable vacuum could be vastly longer than the current age of the universe. This is not a polite way of saying that doom is scheduled for next Thursday. It is a technical possibility inside certain calculations, not a practical forecast for cancelling appointments. The idea of vacuum decay follows from this. If a false vacuum exists, quantum tunneling could in principle allow a transition to a lower energy vacuum state. In simplified terms, a small region could shift into the lower state, forming a bubble that would then expand outward at close to the speed of light, rewriting the local laws and structures determined by the old vacuum. That sounds dramatic because it is dramatic, but it also needs care. This is a theoretical possibility discussed within quantum field theory and cosmology, not an observed process. No evidence suggests that such a transition is underway, and the calculations involved depend on details of particle physics that are not yet fully settled. Still, the fact that physics can even pose the question is remarkable. It means empty space has become something with phases, stability conditions, and the possibility of transformation. The vacuum is no longer just what remains after matter is removed. It is part of the dynamical structure of the universe. The Higgs field enters this discussion in a particularly important way. The Higgs field is a fundamental field in the standard model of particle physics, and its non-zero background value in vacuum is what allows certain particles to acquire mass through their interactions with it. Peter Higgs was one of the key figures associated with this idea, alongside François Englert and several other physicists who contributed to the underlying theory in the 1960s. In 2012, experiments at CERN's Large Hadron Collider confirm the existence of the Higgs boson, the measurable excitation associated with the Higgs field. That discovery was a major triumph for the standard model. Why does this matter for the stability of empty space? Because the form of the Higgs potential, meaning the energy landscape associated with the Higgs field, may help determine whether the present vacuum state is absolutely stable or only metastable. When physicists combine the measured Higgs boson mass with the measured top quark mass and run the standard model equations to extremely high energies, the results suggest something intriguing. Depending on the exact values and the theoretical assumptions used, the universe may sit near the boundary between full stability and metastability. That does not mean the result is simple or final. Small uncertainties matter. New physics beyond the standard model could alter the conclusion. Gravity at very high energies may also play a role in ways not yet fully understood. But the broad reason the idea receives attention is clear enough. The measured properties of the Higgs field seem to place the universe in an interesting position, one where the possibility of metastability cannot be casually dismissed. This gives the subject an unusual emotional tone. It is not horror, and it is not melodrama. It is more like intellectual vertigo. Reality may be built on a vacuum state that feels perfectly ordinary, because it has lasted for billions of years, while still not being the deepest possible ground. The floor beneath everything may be real and stable enough for stars, chemistry, and sleepy conversations about physics, but perhaps not ultimate in the strictest sense. There is no need to overstate this. Scientists are not wandering the corridors of CERN, nervously glancing at the walls in case the vacuum changes before lunch. Theoretical metastability is not an emergency alert. It is a consequence of taking the field picture seriously enough to ask what kinds of vacuum states are allowed and how stable they are under quantum rules. The value of the idea lies in what it reveals about modern physics. Once empty space is granted physical reality, it inherits all the richness and difficulty that physical states can have. It can possess energy, structure, symmetry, and perhaps even alternative versions of itself. That is the deeper lesson. The vacuum is not a blank page beneath the universe, it is part of the text. If there are multiple possible vacuum states, then the laws and properties observed in the world may depend on which state the fields occupy. Masses, interactions, and the behavior of matter could all be tied to the vacuum configuration itself. Empty space would then not merely host reality, it would help define it, and after reaching that edge of the subject, it becomes possible to return with a clearer sense of what all this means on more familiar scales. However deep the theoretical questions become, the central point remains surprisingly concrete. Empty space is not really empty. It shapes particles, light, atoms, forces, and perhaps even the long-term possibilities of the universe. The next step is to bring that idea back down from cosmic and theoretical heights and ask what it means for the ordinary physical world that surrounds everything all the time. After all the talk of quantum fields, vacuum states, cosmic expansion, and the possibility that empty space may be carrying more responsibility than it ever asked for, it helps to come back to the familiar world. A mug on a table, a phone screen glowing in the dark, a beam of light crossing a room, a metal spoon warming in tea, ordinary things, solid things, the sort of things that seem very far removed from discussions about the vacuum, and yet they are not removed at all. They are built on the same framework. That is one of the strangest and most important parts of the story. Empty space is not a separate exotic topic tucked away in the attic of theoretical physics, surrounded by dusty equations and people who have not seen daylight in a while. It is part of the hidden infrastructure of ordinary reality. The behavior of atoms, the structure of chemistry, the emission and absorption of light, the properties of materials, and the operation of modern technology all depend on the same field-based picture that turned empty space into something more than absence. Take the atom again, because the atom is where so many large ideas quietly become practical. An atom is not a tiny solar system sitting in a dead vacuum. It is a quantum system shaped by fields, by allowed energy states, by electromagnetic interactions, and by the fact that the vacuum of those fields is not trivial. Electrons occupy quantized states. Light is emitted and absorbed in discrete ways. The possible transitions depend on the structure of the electromagnetic field and on the quantum rules that govern matter. None of this works properly in a picture where empty space is just a blank nothing. Spontaneous emission is a perfect example. An excited atom does not need a visible little shove from the outside world in order to emit light and fall to a lower energy state. The quantum vacuum of the electromagnetic field is already part of the story. That means that what appears to be darkness around an atom is not physically featureless. The surrounding vacuum state matters. It helps define what transitions are possible and how radiation is produced. Light itself, one of the most ordinary things in human experience, carries the imprint of the vacuum in its behavior. Chemistry depends on this deeper structure too. Chemical bonds are not little hooks that atoms politely use to hold hands. They arise from quantum mechanics, from electron states, from electromagnetic interaction, and from the allowed configurations of matter under the laws of quantum theory. The periodic table works because electrons occupy structured states in atoms. Molecules form because those states combine in lawful ways. The carbon in a pencil, the oxygen in the air, the sodium in seawater, and the iron in blood are all behaving according to principles that make no sense in a universe of simple hard particles floating through inert emptiness. The field picture is not optional decoration. It is the actual framework beneath the visible world. The same applies to materials. Solids feel solid not because matter is full in some simple classical sense, but because quantum states, electromagnetic repulsion, and the exclusion principle prevent atoms from collapsing into one another. A wooden table feels firm because of quantum mechanics and field interactions, not because matter behaves like tiny billiard balls stacked tightly together. The familiar world, strange though it may sound, is already a vacuum-dependent and field-structured world. It simply does not advertise the fact at breakfast. Modern electronics rely on this constantly. Semiconductors, transistors, lasers, light-emitting diodes, and quantum sensors all operate through principles grounded in quantum physics. Band structure in solids, electron transitions, tunneling, and photon emission are not engineering tricks laid on top of reality. They are direct uses of the way reality already works. Engineers may not need to say the phrase vacuum structure every morning before coffee, but the theories supporting electronics, spectroscopy, and precision measurement are built within the same quantum field framework that makes empty space physically meaningful. Spectroscopy is especially revealing. By measuring how atoms and molecules absorb and emit light, scientists can probe their energy levels with extraordinary precision. Tiny shifts, splittings, and broadenings in spectral lines reveal interactions so subtle that the old classical picture simply cannot account for them. The Lamb shift is one example, but it sits inside a much broader culture of precision physics in which the fine details of matter continually confirm that the vacuum is not passive. The background is part of the measurement. Even the idea of a ground state, which sounds abstract at first, turns out to be deeply practical. A ground state is not merely a mathematical minimum. It is the baseline from which physical behavior unfolds. The vacuum is a ground state of fields. Atoms have ground states. Materials have ground states. The lowest available configuration of a system matters because it defines what excitations, emissions, and interactions are possible above it. Once that is understood, the whole universe begins to look less like a collection of objects sitting in empty space, and more like a hierarchy of states layered on top of deeper physical conditions. That is really what this entire journey has been replacing. At the beginning, emptiness looked like absence, a missing thing, a clean gap, but little by little that picture gave way. First came the vacuum of classical experiment, where air could be removed and pressure could be measured. Then came fields, showing that a region without matter could still contain real physical quantities. Then relativity gave space geometry and dynamical behavior. Then quantum theory refused to allow perfect stillness. Then quantum field theory showed that particles are excitations of fields whose vacuum states remain present everywhere. Then experiments revealed that this vacuum could shift forces, alter atomic energies, and influence radiation itself. The pattern is remarkably consistent. What looked like silence turned out to contain structure. What looked like absence turned out to contain conditions. What looked like nothing turned out to be one of the most important somethings in physics. And that does not make the everyday world less ordinary in any disappointing sense. It makes it richer. A lamp glowing on a desk is still a lamp. A warm cup of tea is still a warm cup of tea. A phone screen still lights up with the same suspicious confidence at 2 a.m. But behind these ordinary things lies a reality in which fields extend through space, ground states matter, and the vacuum is part of the physical framework supporting everything else. So empty space is not really empty in the same way a foundation beneath a house is not really nothing just because it is hidden from view. It is quiet, yes. It is easy to ignore, certainly. but it is doing more than it first appears. And the ordinary world, far from standing apart from that fact, depends on it every moment. By this stage, the phrase empty space is not really empty has gathered quite a lot of baggage. Some of that baggage is useful, some of it is not. And because the topic has a habit of attracting both genuine wonder and enthusiastic misunderstanding, it helps to pause and separate what modern physics actually says from what people sometimes wish it said after 3 documentaries and half a motivational podcast. What physicists mean is precise. In modern quantum field theory, the vacuum is not defined as absolute nothingness. It is defined as the lowest energy state of the relevant quantum fields. Those fields remain part of reality even when no ordinary particles are present. Their vacuum states can influence measurable outcomes. That is the core scientific claim. It is grounded in mathematical theory, tested indirectly through specific physical effects, and discussed within a very disciplined framework. What physicists do not mean is that empty space is a magical warehouse of unlimited free energy, waiting for someone with enough confidence and a suspicious website to plug in a cable. The vacuum is physically meaningful, yes. It has structure, yes. But that does not mean it can be mined like a cosmic oil field. Zero-point energy is a real concept in quantum theory, yet that does not translate into a practical invitation to power cities with emptiness and a strong personal brand. They also do not mean that particles casually appear from perfect philosophical nothing in the everyday sense. That phrasing is often used loosely, especially in popular science, because it captures part of the strangeness. But taken too literally, it becomes misleading. The better statement is that quantum fields possess non-trivial vacuum states, and that the mathematics of those fields includes fluctuations, correlations, and interaction terms that can affect physical processes. That is subtler than saying things pop into being from nowhere, but it is also more accurate. The distinction matters because the real science is already strange enough. It does not need extra decoration. Empty space in physics is not mystical emptiness, spiritual blankness, or a metaphysical canvas waiting for intention to scribble on it. It is a technical concept defined inside theories that make precise predictions. Those theories are checked against experiment. When they fail, physicists notice, usually with equations first, and then with a level of professional concern that only later turns into coffee. That is what keeps the subject anchored. The vacuum is not accepted because it sounds profound. It is accepted because quantum field theory works. Quantum electrodynamics predicts measurable effects such as the Lamb shift and agrees with experiment to astonishing precision. The Casimir effect shows that the vacuum responds to boundaries and geometry in experimentally relevant ways. Particle physics at CERN and in major university laboratories relies on field-theoretic descriptions in which the vacuum is part of the formal structure, not a poetic flourish added for atmosphere. This wider scientific community matters. Ideas about the vacuum are not judged by how dramatic they sound in isolation. They're evaluated through peer-reviewed theory, accelerator experiments, atomic measurements, cosmological observations, and decades of work across institutions such as CERN, national laboratories, and university physics departments around the world. The subject belongs to modern science in the most ordinary and rigorous sense. It is argued over, tested, refined, and constrained by evidence. That also means there are limits to what can honestly be claimed. Physicists do not yet possess a final unified understanding of vacuum energy, gravity, and the cosmological constant problem. They do not know with certainty whether dark energy is literally vacuum energy in the simplest sense. They do not know whether the present vacuum state is absolutely stable in the deepest possible way. But uncertainty in science is not a license for fantasy. It is a boundary marker. It tells where solid knowledge ends and open questions begin. So the clearest version is also the calmest one. Empty space is not really empty, because the universe is described by quantum fields that remain present even in their lowest energy states. Those states are not classically trivial. They can influence particles, atoms, forces, and perhaps cosmic evolution. That is already a remarkable conclusion. It does not require mystical language, and it does not require exaggeration. In a way, that makes the truth more satisfying. The vacuum is not interesting because it lets anything be imagined. It is interesting because it is precisely constrained and still deeply strange. It has measurable effects, but those effects arise within careful theory and experiment. It stretches intuition without abandoning reason. And once those misunderstandings are cleared away, the central statement becomes easier to hold on to without distortion. Empty space is not really empty does not mean nothing means anything. It means that what appears empty, under modern physics, is a real physical state with structure, laws, and consequences. That is the sense in which the universe has quietly replaced absence with something far richer. At the beginning, nothing seemed easy to understand. A room could be empty, a shelf could be bare, space could look black, silent, and vacant. In ordinary life, that is usually enough. The mind does not need a theory of quantum fields to recognize an empty cup or an empty street at night. The everyday meaning works because it is practical, and practical language is often happily imprecise. Physics, though, has a habit of pressing on those familiar words until they become less comfortable. Empty turned out to be one of them. At first, the change was modest. The old philosophical idea of the void gave way to the more careful physical idea of a vacuum. A space could be cleared of air, pressure could be measured, and emptiness could become part of experiment rather than argument. Even then, absence had already started to acquire structure. Later, classical physics treated space as a real background, a stage on which bodies moved and forces acted. Then, James Clerk Maxwell filled that stage with fields, and Albert Einstein made the stage itself dynamic by replacing rigid space and time with space-time that could curve, expand, and ripple. That alone was enough to make emptiness less empty than intuition preferred. But quantum physics carried the idea much further. Max Planck, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and the later builders of quantum field theory gradually replaced the old picture of little objects drifting through blank space with something deeper and stranger. The universe came to be described in terms of fields extending throughout space, with particles understood as excitations of those fields. In that picture, the vacuum is not the absence of reality. It is the lowest energy state of something real. That is the central revision. Empty space is not a hole in the universe, it is a physical state. And once that step is taken, the rest follows with a certain unsettling consistency. The lowest energy state does not mean perfect classical stillness. 0-point energy means the ground state retains irreducible structure. Vacuum fluctuations, described carefully, reflect the restless quantum character of those fields. The Casimir effect shows that geometry and boundary conditions can alter the vacuum in measurable ways. The Lamb shift and spontaneous emission show that the vacuum is woven into atomic behavior. Cosmology suggests that tiny quantum irregularities may have been stretched across the early universe and helped seed galaxies. Dark energy raises the possibility that empty space is tied not only to the microscopic world, but to the accelerated expansion of the cosmos itself. So what began as a question about nothing ends as a question about reality. That is part of the philosophical weight of the subject, though the weight remains scientific rather than mystical. The vacuum forces a revision of what counts as absence and what counts as substance. Human intuition tends to grant reality most easily to things that can be touched, seen, and pointed at. A chair feels real. A stone feels real. A beam of sunlight feels real enough when it lands across a wall. Empty space, by contrast, feels like what remains when the real things have been removed. Modern physics does not fully permit that distinction. The vacuum may not be a thing in the everyday sense, but it is still part of what the world is made from. That does not mean every question has been settled. Far from it. The relation between vacuum energy and dark energy remains one of the deepest unresolved problems in theoretical physics. The cosmological constant problem stands as an enormous mismatch between quantum expectation and cosmic observation. The full union of quantum field theory and gravity remains incomplete. Even the stability of the vacuum, especially in connection with the Higgs field and the Standard Model, remains a subject of careful theoretical discussion rather than final certainty. That uncertainty matters, and it deserves calm honesty. The vacuum is not fully understood in the deepest possible way. It is measured indirectly, described with extraordinary success in some contexts, and still mysterious in others. Science is strongest when it says both of those things at once. The known must be stated clearly, and the unknown must remain genuinely unknown. Even so, enough is known to change the picture permanently. Empty space is not really empty in the classical sense. It has geometry under relativity. It has fields under modern particle physics. It has ground states, constraints, effects, and consequences. It shapes what happens to atoms, particles, light, and perhaps the universe itself. It is quiet, but not blank. It is subtle, but not absent. There is something deeply satisfying in that. The places that look most barren often turn out to be the most revealing. A dark stretch between stars appears empty until physics begins asking better questions. Then the darkness fills with structure. Then silence becomes law. Then nothing becomes one of the richest ideas in science. And perhaps that is the final shift worth carrying forward. The vacuum is not interesting because it violates reason. It is interesting because reason, when followed carefully enough, leads directly into it and finds far more there than intuition expected. What appears empty is not a failure of reality to contain something. It is one of the clearest windows into how reality is built. So why is empty space not really empty? Because in modern physics, the vacuum is not a literal absence of all structure. It is a physical state of quantum fields, the lowest energy condition of a universe still full of underlying reality. What looks like nothing is, in fact, a lawful, structured, and active part of the world. The journey to that idea has been a long one. It began with philosophical arguments about the void, moved into laboratory vacuums shaped by pressure and experiment, passed through relativity where space became spacetime with geometry and motion, and then entered quantum theory, where uncertainty, fields, and zero-point energy made perfect stillness impossible. From there came fluctuations, measurable effects like the Casimir effect and the Lamb shift, and even the possibility that the vacuum helped shape the large-scale structure and expansion of the cosmos. None of this requires fantasy. It does not ask for mysticism, only careful attention. The strange richness of empty space comes from science itself, from theories tested against experiment and refined through observation, and that may be the quiet beauty of it. The most silent parts of the universe may also be among the most revealing. In what appears to be nothing, physics finds the hidden framework beneath particles, light, matter, and cosmic history. Nothing, it turns out, is rarely simple, and the closer observation moves toward true emptiness, the deeper reality seems to become.